Hello. This time we're going to look at how this concept of linearity and superposition can be applied to circuits which are not linear. This may sound like a contradiction, but actually it provides a very useful technique called the small signal approximation. The best example of a nonlinear component that we've seen so far is the diode. Now, as we'll know, the current through a diode is not proportional to the voltage across the diode. It ends up looking more like an exponential curve like this. However, if you just look at a very small range of voltages across the diode and a very small range of currents through the diode, then this curve can be approximated by a straight line. And a straight line that goes through what's known as the operating point of the circuit. This approximation is only valid for very small changes in voltage and very small changes in current, but provided the circuit is not moving very far from its operating point, we can consider that the change in current is proportional to the change in voltage. And in this way, the diode is behaving like an approximately linear component, approximately like a resistor. The change in the voltage across the diode is proportional to the change in the current through the diode. The total voltage across the diode is not proportional to the total current through the diode, but for small changes, the change in voltage is proportional to the change in the current. We can approximate that characteristic by a straight line. And instead of a straight line passing through the origin, as it would for a resistor, it passes through the operating point. So it's the distance from the operating point in voltage that is our input, and the distance from the operating point in current that would be our output in this case. And then we can apply superposition. For example, supposing I had two components which were changing the voltage across this diode. One of them causes a change in voltage of delta V1 from the operating point, 700 millivolts, down to V1. I'm writing that change as delta V1. Delta V1 is negative in this case because V1 is smaller than 700 millivolts. And another source in the circuit which was causing a change in the voltage from 700 millivolts up to V2. I could represent that change in voltage as delta V2. The effect of the first change in voltage is to cause a change in current of delta I1. The effect of the second change of voltage is to change the current by delta I2. So superposition, which I can use over this small range of voltages and currents because I do have a straight line here, and my straight line goes through the point that delta V equals 0 gives delta I of 0, then I could say that the total voltage difference from the operating point, due to both of these sources, both of these effects, would produce total change in current, which is the sum of the two changes in currents. We'll see an example of this in the next video. In the remainder of this video, I just want to introduce two new terms and another definition of linearity that we sometimes use. The first of the new terms is static resistance. The static resistance is the total voltage across a component divided by the total current flowing through that component. So, for a diode like this, the static resistance would be 1 over the gradient of this dotted blue line. 1 over the gradient because this graph has current on the y-axis, so the gradient would be current divided by voltage. Current divided by voltage is 1 over resistance. You can see that the static resistance is a function of the operating point. At high values of current, the gradient will be steeper, which implies a lower static resistance. At low values of voltage, the gradient would be much shallower, which implies a much greater value of static resistance. For example, supposing we had something like this, and this was our 700 millivolts, and that point there was 800 millivolts, and this point, say down here, about 300 millivolts. That's not a very accurate representation of what diodes do, but it will do for my purposes at the moment. This is delta V, the voltage across the diode. This is the current flowing through the diode. If at 700 millivolts we have 10 milliamps going through the diode, and at 300 millivolts we have 1 milliamp going through the diode, and at 800 millivolts we have 1 amp going through the diode, then the static resistance at 700 millivolts would be equal to 700 millivolts divided by 10 milliamps, which is 70 ohms. The static resistance at 800 millivolts, however, would be 800 millivolts divided by 1 amp, which is 0.8 ohms. And the static resistance at 300 millivolts would be 300 millivolts divided by 1 milliamp, which is 300 ohms. So you can see that the static resistance is getting much smaller as the voltage across the diode and the current flowing through the diode are increasing. Static resistance is often defined in contrast to dynamic resistance. Dynamic resistance is defined in terms of the gradient of this graph at any point. Since the graph is current on the y-axis, the dynamic resistance is actually the inverse of the gradient of this curve at any point. So it's the dynamic resistance that is the constant when we're using the small signal approximation. The dynamic resistance is defined as the change in the voltage divided by the change in the current for a small change of voltage and a small change of current. For those of you who like calculus, that's dV dy, the rate of change of the voltage with current at the particular operating point. Neither of these two quantities are constant. They both vary as the current through the component or the voltage across the component change. Or at least that's true for any nonlinear component. You can prove that if the static resistance is equal to the dynamic resistance, then you have a resistor. Because for a resistor, these two quantities are equal, and they're just equal to the resistance of the resistor. It's quite a neat little proof if you're interested. Dynamic resistance, dV by di. The static resistance is the voltage V over I. Therefore, dV over V must be di over I, which gives you that log of V must be log of I plus a constant, and therefore V equals K times I, or K dash. It's not the same constant, but V equals K times I, taking the antilog of that. And that is the voltage is proportional to the current, and that's only true for a resistor. Final topic in this talk is the concept of piecewise linearity. Sometimes when we don't have an algebraic expression for the relationship between the current and the voltage through a component, we approximate the empirically measured relationship by a series of straight lines. In this case, we have a dynamic resistance which is constant over a certain range. It's another approximation, but this is the approximation that is used to represent Zener diodes in breakdown in the quiz app. Okay, that's all for this time. Final one of these talks about linearity, and we'll be doing a real example showing how to use the small signal approximation.